All right, let's talk about electricity. We're going to take this thing that feels, well, kind of invisible and mysterious, and turn it into something that just makes sense. Something you can actually see in your head.
So, where do we even begin? Well, first things first, we've got to bust a pretty common myth. Because honestly, the way most of us think about electricity, it's probably all wrong. And it's what stops us from really truly getting it.
Most of us, right? We think of electricity as just pure energy zipping through wires. But that's not the whole story. It's actually much more useful to picture it as the movement of tiny little charged particles. See, it's not the energy itself that's flowing, it's the stuff carrying the energy.
Okay, so if we're going to understand that movement, we need to meet the main character in this whole story, and that is the electron.
You know, deep inside every atom, you've got protons with a positive charge and neutrons, which are, well, neutral. But for our story, the story of electricity, the real stars are the electrons. These little guys have a negative charge, and they're zipping around the outside. And here's why they're so important. They're the ones that can actually break free and jump from one atom to the next, especially in stuff like metal.
Okay, so we have all these electrons moving around. It sounds complicated, right? But what's so cool is that we can understand all this complex behavior using a really simple idea, an analogy you're already super familiar with. Just think about water flowing through pipes.
First up, let's talk about current. What is it? It's just the amount of charge, the number of electrons flowing past a certain spot. In our pipe analogy, this is just like the amount of water flowing through. You know, more water equals more flow. It's the same thing here. More electrons moving means more current. Simple as that.
But, you know, those electrons don't just decide to move on their own. Something has to push them along, and that push is what we call voltage. Back to our water pipes, voltage is just like water pressure. The higher the pressure, the harder the water gets pushed. Same deal with electricity. Higher voltage gives those electrons a bigger push.
All right, so as our little electrons are getting pushed through the wire, they're not on a perfectly clear highway. They're constantly bumping and crashing into the atoms of the wire itself. This creates a kind of, well, electrical friction. We call it resistance. And in our pipe analogy, this is like a really narrow part of the pipe, or maybe one that's a little clogged up. It just makes it harder for the water to get through.
And all of this comes together to show this really elegant relationship between these three things. It's actually a famous rule called Ohm's law. Think about it. If you increase the voltage, the pressure, you're going to get more current, more flow. But if you increase the resistance, that friction, you're going to get less flow. It's this perfect little balancing act. And this isn't just some abstract idea, okay? This one simple rule governs everything electrical, from the light bulb in your lamp to the most powerful computer on the planet.
Okay, so this brings up a really interesting question, a bit of a puzzle. We know that individual electrons actually drift through a wire pretty slowly. So how come when you flip a light switch, the light comes on instantly?
Yeah, it's a great question, right? And the answer is super cool. It's all about understanding the difference between the signal and the electrons themselves. See that push we talked about? That signal to get moving? That travels down the wire at almost the speed of light. But the actual electrons? Yeah, they're just kind of shuffling along at a snail's pace.
I love this way of thinking about it. Picture a really long, crowded line of people, all packed together. If the person at the very back gives a shove to the person in front of them, that push travels through the whole line almost instantly. The person at the front feels it right away. But did anyone in the line actually walk very far? No, they just shuffled a tiny bit. And that is exactly how electricity works in a wire.
Okay, so for that push, that signal to actually travel, it needs a complete unbroken path. And this brings us to the actual stuff our electrical systems are made of. You know, the materials that make everything work, all the way from the giant power plant down to the lamp on your desk.
It turns out some materials are basically wide open highways for electrons. We call these conductors. Think of metals, like copper. Electrons can just cruise right through. But then you have other materials that are like solid brick walls. They stop electrons dead in their tracks. We call those insulators. And that's exactly why your power cords are wrapped in rubber or plastic. It keeps that electrical highway safely contained.
And believe it or not, this is all a light switch does. It's not some kind of magic box. When the switch is off, all it's doing is creating a break in the highway. It's what we call an open circuit. But when you flip that switch on, boom, it closes the gap. It connects the road. Now you have a closed circuit and the electrons have a complete loop to travel around.
So why does any of this matter?
Well, here's the crucial part. When those electrons are flowing through that nice, closed loop, they can actually do stuff for us. This is the whole reason we bother with electricity in the first place. We're turning that flow into something useful, like light to read by, or the power that charges your phone.
And that work that gets done, we have a name for it: power. Power is simply what happens when the energy from all those moving electrons gets converted into some other kind of energy. You know that warmth you feel coming off your phone charger? Or the light from a light bulb? That's power in action. It's the electrical energy being transformed into heat or light, right there inside your device.
Okay, so let's recap the whole thing. You've now got the complete picture. Electricity isn't some weird abstract energy. It's just moving charge. Voltage is the push that gets it going, resistance is the friction that tries to slow it down, and it all needs a closed loop, a circuit, to even work. So by using these simple ideas, water in pipes, crowds of people, you've basically learned how to see the invisible. You can now picture this system that powers our entire world. You've pretty much decoded it. And that leaves just one question. Now that you have this new way of seeing things, what are you going to understand next?